Hello, hello my loves. Right, we're going to do all of differentiation now. So what we're going to start with is we need to make sure you know absolutely everything here. So we start with the basics. So obviously y equals x, so dy by dx would just be 1. Right, okay, so here I'm going to, instead of writing dy by dx, I'm just going to say it goes to 1. All right, just to save time. Obviously now you know that one. So and then obviously x squared goes to 2x, that's easy, and so on. Right, if we have the power on the bottom though, so say you have 1 over x squared, then you're going to bring that up, so that's equal to x to the minus 2, and then when you differentiate that, you multiply by the power, knock 1 off the power, and then obviously that can go to minus 2 over x cubed. Now, where people go wrong a lot is if we have, say, y equals 1 over 3x squared, or something like that, they try and bring the 3 up as well, but really that's the same as a third times 1 over x squared. So when you differentiate that, you get a third times what you'd get if you differentiated 1 over x squared, which is minus 2 over x cubed as just shown. So when you multiply the top, you multiply the bottom, you get minus 2 over 3x cubed. So be very, very careful. Right, what about if y equals the natural log of x? Okay, well, hopefully you know that that goes to 1 over x when you differentiate it. But what people do very wrong sometimes is they say, right, if y equals the natural log of 3x, they forget that you need to differentiate what's in the bracket. Because really, if y equals the natural log of some function of x, so that could be x, 1 over x, 3x, x squared plus 4, whatever, when you differentiate that, you get the bracket, well, the function differentiated over what actually is the function. So f dash x over f of x, that is your dy by dx. So say you had something like the natural log of, well, say it was the natural log of sine x. Ooh, that's nasty. So the natural log of sine x, you differentiate your bracket, that would give you cos x, and that would go over what was originally in the bracket. What's your original function? So that would be cos x over sine x. And as you all know, that's the same as cot x. This is actually in your formula book. It's the one that everybody always forgets. It's here. It's this one. Remember, differentiation is just integration backwards and vice versa. So if we are differentiating the natural log of some function of x, we get the function of x differentiated over our f of x on the bottom. So that's one that people do wrong quite a lot. So say you had something like natural log of x, let's say x squared plus 4x plus 4, no, let's go plus 3. Then obviously you're going to differentiate this and you'll get 2x plus 4. That's what goes on the top. And then on the bottom, you get that original function, x squared plus 4x plus 3. Okay. What about if you're doing 3 times the natural log of something? Well, just like with any differentiation, when you differentiate it, you're just going to get 3 times whatever the function differentiated is. It's only when the 3 is on its own that it disappears. So this is 3 times the natural log of x. So we're going to get 3 times 1 over x here when we differentiate, because natural log of x goes to 1 over x, and that will give you 3 over x. Okay? Whew! But what about, oh right, I've not differentiated the natural log of 3x here, have I? So the natural log of 3x, differentiate the bracket, you get 3, goes over what is in the bracket, so over 3x, which is the same as 1 over x. Sorted. Right, what about everyone's least favourite function, x root x? Well, that's the same as x to the power 1 add a half, so x to the power 3 over 2. When you differentiate that, you multiply by the power, knock 1 off the power. Okay, so you get 3 over 2 x to the half. Now, if it was 1 over x root x, if that was your f of x, then when we differentiate that, we're going to have to bring that up as x to the power minus 3 over 2, and then differentiate it. That's equal to x to the minus 3 over 2. Differentiate it, multiply by your power, knock 1 off your power. Be careful, minus 3 over 2, take away 1 is minus 5 over 2. And if you're having somebody asking you to do this in a certain form, you might need to take this power here down There we go, like so. And then we're just back to multiplying fractions again. Minus 3 over 2x, so the 5 over 2. Okay, right, now what about, by the way, I've put the bit of your formula book here on the side. It's very, very useful, this, especially if you know that you can go from the right-hand side to the left-hand side here to integrate. So if you integrate sec squared x, you get tan x. If you integrate minus cosec squared x, you get cot x. Just the same as it works that way for differentiating. And the same is true for the integration bit. Okay, if you integrate that, you get that. If you differentiate the right-hand side, you'll get tan x. Okay, so it works forwards and backwards. Right, so that's logs and rational powers. Okay, let's try something else. What about your e's? Right, so say your function is e to the x. Now, obviously, when you differentiate that, you still get e to the x. So dy by dx is also e to the x. But what if it was e to some function of x? So let's say your y was e to the 3x plus 1. So we differentiate. What we're actually doing here is we're differentiating the power here and we're timesing by that. So if we differentiate x, we just get 1. So obviously we just get e to the x. Now here, we differentiate the power and we get 3. Okay? So, and then the power stays the same. We don't do anything to it. So it's still e to the 3x plus 1, but this time we're multiplying it by that power differentiated. So what about if you had y equals e to the sine x? Well, it's exactly the same. You differentiate that power and that would give you cos x, and then your e would stay the same with the power the same. So you get cos x e to the sine x. Not very nice, but it's true. Okay, what about, right, y equals 2 to the x. Okay, so if we differentiate that, this is the special case that you need to remember, you get 2 to the x ln 2, or 2 to the x times the natural log of 2. Now, don't be scared of this. The natural log of 2 is just a number. Okay, so if you were going to integrate 2 to the x, now don't be scared of integrating 2 to the x. We know we want to integrate 2 to the x ln 2, or 2 to the x times the natural log of 2, and that will take us back to 2 to the x. But if you were integrating 2 to the x, we haven't got this ln 2. We've actually got this divided by ln 2, if you can think of it like that. So really, if we divide that by ln 2, then when we integrate this 2 to the x, which we know we get 2 to the x ln 2. Okay, but we're dividing it by ln 2. So what you really get when you integrate 2 to the x is 2 to the x over ln 2. That's what you really get. Have I just confused everybody there? Probably have. I'll do it again. I'll do it again properly, because that was a bit confusing. Confused myself. Right, hang on. Because this is probably one of the harder ones that you'll ever do. Right. Let me get a blue. Blue's always a good colour for maths. Right. If we integrated 2 to the power x ln 2, then we know we would go back to 2 to the x. Okay? Because if we differentiate 2 to the x, we get 2 to the x ln 2. So if we were just integrating 2 to the x without this ln 2 with it, then we wouldn't get 2 to the x ln 2. We'd get 2 to the x over ln 2. Okay, now to check what on earth Louise is on about right now, if you think, right, I'm going to check that this is right. So what I'm going to do is say I'm going to differentiate 2 to the x over ln 2. Okay, and you know that if you differentiate that, you get 2 to the x ln 2, and we're still dividing that by ln 2. So they go away, and you're just left with 2 to the x. Does that make sense? Hopefully it does. Okay, so that's our what we're doing here. Linear, power, rational, done that. Exponential, done that. Logarithmic, we've done that. And sinusoidal. So let's just have a quick look at the trig functions. So, trig functions, we've got, so say we've got sine x. No, we've done that. Sine x goes to cos x and so on. And we know we've got the wheel of differentiation. Sine x goes to cos x goes to minus sine x, and that goes to minus cos x, and then we're back to sine x again. Right, so the only time this could get tricky is if you've got more than one x. So say you've got sine of 3x. Okay, so when we're differentiating, you're going to differentiate this x term here, and which gives you 3. And your sine goes to cos, so we end up with cos 3x. So this angle here, this 3x stays the same, but we just differentiate it to get that 3 there. So really, if we've got sine of f of x, some function of x, then that goes to differentiate that function, and then sine goes to cos, and then it's cos of that function, that f of x. Okay? Right, okay, now the same with cos. If you do cos of 4x, you'd get minus 4 sine 4x, because we're going around the wheel of differentiation, which is why you multiply when you're differentiating, but you divide these when you're integrating. Now remember, some of these are in your formula book. You've got your sec, cosec, cot there, and then your natural log of your trig functions there as well. So watch out for those. Okay, so that's pretty much all of differentiation, I think. I'm trying to think, have I missed anything? Hopefully that's helped. If I have missed anything, give me a shout and we'll see what we can do about that for you. Now, I'm just thinking, differentiation from first principles, make sure you can do it. Might come up, you never know. Okay, right, further differentiation. Let's think, we've got two things. If you're trying to differentiate two different functions, so say you had 2 to the x times, I don't know, sine x, something like that, then you'd have to use product rule. So product rule is little shout out to my little Will there. So u dash v plus uv dash. Oh no, it was Callum. U dash v plus uv dash. Okay, and that's u. Your first one is u, your second one is v. And then you put them together like that. You've got your quotient rule. So say you've got y equals x cubed times e to the x, something like that. Talking rubbish, hang on. Quotient rule. You've got to be dividing by it. Sorry, it's been a long day. So x cubed over e to the x. So this time you say the function on the top is u, function on the bottom is v, and you put them together using u dash v minus u v dash all over v squared, and that bit is in your formula book anyway. Okay. Now sometimes you'll get something that you think you can't differentiate. So, well, you can pretty much use quotient rule for anything. I'm trying to think. No, it's more integration. I'll talk about that when we come to integration. So we've got that and we've got that. So we've got product rule and we've got quotient rule, which are pretty important. And I can't think of anything else right now. But again, if you can think of something, tell me. Bye.